will be chaired by Professor Shimomura. So he is an expert in self-assembly of organic molecules on surface of inorganic crystals and its applications. So he also works on imaging by 3D photo electron holography and X-ray fluorescent holography. So three-dimensional atomic imaging by photoelectron holography and fluorescent X-ray holography. So theoretical calculations are also a part of his work. So he works on electronic structures and nanomaterials. So his research is mostly published in high reputed journals. So I would like to welcome Professor Masaru Shimomura from Shizuoka University, Japan to chair this session. Thank you, sir. Over to you.
Thank you very much for the kind introduction. My name is Masaru Shimomura from Shizuoka University. So I would like to guide the session 1G as a chairperson. And the first presentation will be given by Professor Daniel Morel from Shizuoka University. And I would like to give a brief introduction of him. And Professor Daniel Morel is associate professor of Research Institute of Electronics, Shizuoka University. And current his research interests are in the silicon nano devices and single dopant devices. And he received several awards, for example, Young Researcher Awards, SSDM, Young Scientist Oral Presentation Award, JSAP, and Young Scientist Gold Award, IUMRS ICEM, and so on. So Professor Morel's presentation title is Band-to-Band Tunneling in Highly Doped Silicon on Insulator Nanoscale Esaki Diodes. So could you start the presentation, Professor Morel? Professor Morel, check out the microphone.
Rene?
Please unmute the microphone.
So we are doing actually. We'll allow. Okay. Yeah.
Right.
Okay, I think now it works.
Yeah.
Yes,
okay,
please.
it was forbidden from before. Okay, can you hear me? So thank you, Professor Shimomura, for the kind introduction. And let me share my slides. Just 1 second. Okay. So can you see the full screen now?
Okay, we can see.
Okay.
Yeah, thank you.
Okay, so it's really a great pleasure to be able to give a talk in ICONN conference again after some break. It's unfortunate that we have to do it virtually and not live face to face, but it's definitely a nice chance to share our research with a nice network at SRM. So this work is actually a collaboration with Gaurang Prabhudesai, and he originally comes doing his master in SRM. So it's really nice to have this kind of extended network, and the results are mostly and in big part thanks to him. So today we will talk about the following topics. I would like to first introduce the basic concept that we are going to discuss, which is band-to-band tunneling in Esaki diodes mainly. And this will be split into two parts, and one part will be dedicated to the band-to-band tunneling via dopant-induced energy levels. We report in silicon-only insulated tunnel diodes that we observe some current enhancement, which is, in our interpretation, due to donor-acceptor pairs, so kind of an atomistic effect in nanoscale Esaki diodes. And the second effect is band-to-band tunneling of charges, even one by one, mediated by dopant-induced quantum dots. So we will discuss about the likelihood of observing this kind of quantum dots, and also how do we judge that we are dealing with single charge tunneling in such devices. So finally, a more recent result is not only on the high doped diodes, but also on low concentration diodes. I will report just on the possibility of band-to-band tunneling, in this case by tuning the substrate voltage. And then I will summarize and conclude my talk. So to start from the beginning, is this talk is completely about quantum tunneling, and we take generally quantum tunneling as granted nowadays. We know that it appears in tunnel diodes and tunnel field effect transistors, or even in regular transistors. But the beginning of these applications in practical devices comes from this paper of Leo Esaki in 1957, which was entitled New Phenomenon in Narrow Germanium PN Junctions. As you can see, this is his hand drawing showing that by doing high concentration p-type and high concentration n-type, we create degenerate levels inside the bands, and we can allow band-to-band tunneling through this narrow depletion layer. So Leo Esaki is here. He received a Nobel Prize for this work and others related. And the typical characteristics of an Esaki diode are shown here. We have a very high current in the reverse bias and a very low current in the forward bias, but with a negative differential conductance peak observed at low voltages. In this case, both reverse and forward current, the vertical axis, are shown on the absolute value of voltage for simplicity. So these are the telltale signs of an Esaki diode, and that was already reported, well, 60 years ago or more. So it's a relatively large device, giving milliampere currents. What happened in the meantime was that about 10 years ago, we get the final reports of silicon nanowire Esaki diodes. And they used CVD technique to create vertical NP wires. And what was observed in these devices was basically, the telltale signatures of Esaki diodes. The negative differential conductance peak in forward bias and the high reverse bias current. It's very nice. We can enter the world of nanoelectronics with these devices, but generally, this gives us a simple scaling down of Esaki diodes. So for further understanding, I'd like to introduce very briefly the basic mechanisms that are going on in the Esaki diode, highly doped P plus N plus diode. So as I've just said, in the reverse current, we have a high current, reverse bias. This is because the narrow junction allows the tunneling of electrons from the valence band into the conduction band states, kind of a center tunneling. In the forward bias, in zone A, because of the degeneracy of both sides, we have a chance for the electrons from the N side to tunnel into available states in the P side. So this is maybe the most important part of the Esaki diode. It is followed by a kind of an unwanted effect, which is excess current. And this is described by tunneling mediated by some traps or defects in the mid-gap. And it is then followed by thermal current at higher biases, just like a PN diode. So the most important part here is basically the band-to-band tunneling that occurs at low forward bias. And this is where we will focus our attention. Because silicon is also indirect band gap semiconductor, we might need also phonons, specifically TA and TO phonons, to assist in the momentum conservation in tunneling. So our question is basically, beyond the simple downscaling of the devices, can we detect any new mechanisms emerging or observable in nanoscale? For example, when we scale down the devices to two-dimensional silicon layers, and we looked at face-to-face boron-doped versus phosphorus-doped areas, couldn't we access signatures due to the atomistic nature of this distribution of dopants or other nanoscale specific effects? So with that in mind, let me show you a couple of results that we observed from various perspectives. So first of all, in order to access this kind of devices, this kind of scale, we fabricate silicon on insulator lateral Esaki diodes with a p-type region on the left and an n-type region on the right, and there is a barium oxide underneath. Silicon substrate can be used as a backgate. It's called here V sub, and this is the equivalent circuit that we are using. Typically, we use silicon dioxide mask to dope N-type, and we use silicon nitride mask to dope P-type. And this kind of technology, built up over several years in our clean room facility, allows us to fabricate p-n junctions in a very thin layer and also relatively narrow. We use the clean room facilities in our research institute of electronics here. And it also allows us to create very high doping concentrations. Both P and N are on the order of 10 to the power 20 per cubic centimeters. They are doped in this case by thermal diffusion doping. We are gradually switching to rapid thermal annealing. But in this case, the donor concentration is higher than the phosphorus concentration, but they are both high enough to justify this picture of a Venn diagram. There is a narrow depletion layer between N and P, both degenerately doped, and the depletion layer width is on the order of 10 to 20 nanometers. Even though the band gap is effectively the barrier height, this still allows significant tunneling rate between the two sides. So we are actually looking at thin SOI Esaki diodes, and we'll report two main results. One is that because of charge confinement in such small scales, we get deepening of the energy states of dopants, and we report this effect in Applied Physics Letters in 2016. And the second effect is because, again, of low dimensionality, we obtain dopant clustering, and it has a significant effect in the transport characteristics. And this was reported in Applied Physics Letters in 2019. So the first observation that we obtained that was quite interesting for us was that of sharply enhanced current peaks. What I'm showing here is a low temperature IP-VP characteristics of some devices. You can notice the relatively high reverse current, reverse bias current, and also the NDC characteristics in the forward bias, as well as the typical PN diode characteristics. What is most peculiar here is actually this enhanced, locally enhanced current peak illustrated here. In other devices, we obtain multiple such peaks, not only one, so we observe several enhancements locally in different positions in VP. So we believe that these are due to the strongly enhanced current peaks observed in several devices of this dimensionality are related to the donor and acceptor deep levels. So let me explain a bit more what this means. In large PN diodes, we expect to have boron acceptors and phosphorus donors in the same region of space, in the depletion layer. But they are both introducing shallow energy levels, about 45 millielectron volts inside the band gap. Now, if we moved in dimensionality from 3D to 2D and eventually to 1D, we could obtain a deepening of both types of energy levels, both acceptor and phosphorus. This is an exaggerated view. Of course, we don't get mid-gap states, but at least a few or 100 millielectron volts or several hundreds of millielectron volts could be achieved. If you also include into this the fact that we have a built-in potential, then you can imagine that we have a possibility to align boron states with phosphorus states, boron on the P side and phosphorus on the N side, and thus create a favorable path for the electrons to move between the bands. So this is what we'd like to identify, and this is what we propose as an interpretation for the results that we observed. The fact that deep dopant states could in fact breach the depletion layer and create these enhanced current peaks. So the results are shown here in different visualizations, basically. The bottom figure shows the IP, VP, in the forward bias, and what is given in the inset is the V sub voltages. When we apply different V sub, we can shift this enhanced current peak left or right as shown by this arrow, and we can also change the intensity of a current peak. On the top, you can see the surface plot, same result, but shown as a surface plot. So we start by interpreting this enhanced peak at point 1 by the alignment of a phosphorus donor on the right and a boron acceptor level on the left. And this allows us to observe this enhancement. But then if you apply some, let's say, more negative VP, then misalignment between these two levels could be obtained because of different coupling of P and B to the VP voltage. However, again, because of different coupling of these two the dopant states to the backgate this time, we can achieve, by moving to point 3, a realignment of the two energy levels in the transport window, and thus we can move back on the peak and we observe the enhancement again. So this kind of shift, utilizing two knobs, let's say, VP and V sub, gives us the possibility to access and tune the atomic level effects in these devices. And this result was published together with Professor Tabe in 2016 in Applied Physics Letters. So this is the experimental representation and interpretation, and we have several devices of this type, but we also look at how we can visualize the impact of a phosphorus-boron dopant pair in nanostructures from a more fundamental approach, that is by ab initio simulations. We collaborate with Professor Mizuta and Professor Manoharan from JAIST on this topic. And actually what we did was to look at a PN diode with a non-doped small layer in between, effectively a PIN diode, in comparison with one which contains a phosphorus and a boron atom in between. The results are quite interesting. For specific configurations of this PB pair, we obtain a locally enhanced current for the case of a PB pair doped the upper case, while this cannot be observed for the PIN diode. So this is not a very robust observation, but it simply illustrates that we can indeed achieve an enhancement of a current, and that gives us also access to the fundamental physics of atomic level PN tunnel diodes. So we are building on this finding from now on, and we're trying, in fact, to understand how really the energy states are created between a phosphorus and a boron in such a small states, such a small scale. It is not very clear, and this is a topic of interest for us. We are generally publishing some results and reporting some results in various conferences, and some students in our group, in collaboration with Professor Nimura's group, are working on this topic as well. So this is the first part, which captures the signatures of atomic level functionalities in these PN tunnel diodes. Now let me also move to the second part, which describes another fundamental observation, and that is band-to-band tunneling of charges one by one, effectively single charge tunneling, as written here, through dopant-induced quantum dots. So we use the similar devices, which are the silicon on insulator, with a silicon substrate working as a backgate. Through this barium oxide, we can control the potential in the depletion layer, mostly because we are using these masks properly. The P side and the N side, as shown here, have very high doping concentrations. They are practically metallic, far above the metal insulator transition. So we are not worried about controlling the potential in these zones. The only successful control that we can achieve with a silicon substrate is effectively in the depletion layer. So we also benefit from the high doping concentration to observe highly degenerate silicon on both sides, P and N, and this justifies the band-to-band tunneling, especially because the depletion layer width is on the order of 10 to 20 nanometers. So one more point that is of interest for us in this case is the following. We are not dealing with very, very small scales between P and N. Indeed, the length of this or the length of the active region is mainly dictated by the depletion layer. It is small. Thickness is also small, on the order of 10 nanometers. But in terms of width, in fact, due to some lack of controllability of a width in these devices, the width is on the order of 100 nanometers. Not very small. But in this dimensionality, we have a mixture of boron and phosphorus, and they will interact with each other in interesting ways to allow us to observe various intriguing observations and experimental results. So let me show two types of characteristics that we obtain from these devices when we characterize them at low temperatures. In the IPVP, this shows those two representative examples from those two types of behavior. So the first one is the black curve. It shows high current in the reverse bias, and again, NDC characteristics in the forward bias, and followed by the PN junction characteristics. What is also most interesting is that we also can observe kinks at specific voltages in the forward bias zone just before the NDC region. And when we take a first derivative of these characteristics, we can emphasize very clearly where these contributions start, and that coincides very well with the energies well known for transverse acoustic phonon. This is about 18 millivolts, 18 milli-electron volts in energy, and respectively transverse optical phonon, which is very near to 60 milli-electron volts. So indeed, as expected for the indirect bandgap silicon, we observe TA and TO contributions to the current in this type of device. So I mentioned before that because we have electrons in the conduction band at a different wave vector and holes in the valence band at a different at gamma point, when the band-to-band tunneling has to be achieved, we have to compensate the momentum difference at least by absorption or emission of phonons. And this is what we're seeing here. Now, more interesting, however, is what we observe in the other type of device, and that is the red characteristics. So in the red type of characteristics, we can see a quite different behavior, and that is a kind of a staircase with very prominent current steps observed at the values very different from those of phonons. So this staircase reminds us of a Coulomb staircase, which is reported for single electron transistors. And therefore, our first interpretation was that while the electron has to tunnel from the conduction band of the N-type into the valence band of a P-type, a dopant cluster may interpose a quantum dot in between. And therefore, electrons go in and out one by one, mediated by this dopant cluster. So that kind of behavior happens for about 50% of the devices. So this is not a unique, exceptional result, but it is actually a quite frequent observation. So to confirm this effect, we had to look at a different type of measurement, and that is called a stability diagram. We measure not only current as a function of Vp, but also as a function of V sub working as a gate. So this is quite noisy behavior. We have a pattern that is very difficult to define very precisely, but this is what happens in the small devices. Nevertheless, we can notice some pattern of half diamonds observed in this behavior, in this kind of characteristics. And we try to reproduce this behavior by looking at the device simulations, single electron tunneling simulations based on Coulomb blockade. We placed tunnel junctions on the left and tunnel junction on the right, characterized by capacitance and resistance. And we use V sub through C sub to control the quantum dot potential. And we succeeded to reproduce up to some point the basic features observed in the experiment, of course, except the noise structures. So this gives us quite a lot of confidence that we are dealing with a Coulomb blockade transport through a quantum dot present in the depletion layer. The IPV subcharacteristics also show this. Current peaks, we are satisfied with a similarity between the experiment and simulation, but we are still dissatisfied with our explanation. We cannot explain everything. We still need to consider a few of these features. But the point is the following. It was difficult for us to understand where the quantum dot is formed because we have very high doping concentration, and this is what we should think about when we have a p-n junction as doped. However, for statistical analysis, we introduced a donor acceptor compensation algorithm, which looks something like that. If boron and phosphorus are relatively far, well, they contribute to the potential landscape. But if they are near each other, we can actually ignore them because their contribution to the potential is minimized by compensation. So we removed this kind of pairs, which are closer than Bohr radius, 2.5 nanometers. And the picture is relatively simplified now. We see a random distribution of donor clusters in between N and P regions. So now we can analyze more easily the statistics, and this is what Garan did extensively. For 100 cases, before compensation, we had thousands of dopants inside the depletion layer. After we introduce the compensation, just 5 to 10% of the donors are left. And then we can start to see that we are dealing with multiple donor clusters here and there between the two zones. So in fact, if you zoom in, the transport at that region could be easily explained by what we said before, single electron tunneling through this cluster. Electrons start from the N region, go inside this cluster, and then go into the P region by band-to-band tunneling. So this result was published in Applied Physics Letters a couple of years ago, and it's part of a PhD thesis of Garanson. So just let me give you a final view into the statistics. We also checked how many donors are contained in such a typical cluster by checking the cumulative count, and as a function of number of donors per cluster from these statistics for different clustering conditions. So basically, we treat the clustering condition as follows. If a phosphorus and the two phosphorus donors are close to each other, they are treated as a cluster beyond this condition. If they are further apart, then we treat them as individual donors. We were looking actually for a fraction of about 50% of the devices to observe the typical yield that we observed in the experiment, and this 50% is kind of guaranteed by donor clusters that are 5 to 10 donors inside. They contain 5 to 10 donors. So this gives us a possibility to analyze the structure of the quantum dots themselves. Now, the next plan is to make a selective doping of few donor molecules and introduce the SCT as a main mechanism in tunnel nanodiodes. So maybe just in 1 minute, I'd like to give a different view. So considering what we have just shown from the statistics, we should probably consider that there are many cases when a phosphorus donor quantum dot can be interpolated between P and N regions, and it gives us access to very fundamental mechanisms. However, so far I've talked about high concentration devices. If I can take 1 more minute, I'd like to very briefly introduce low concentration devices. Low concentration diodes are quite different because the depletion layer width is relatively large. Band-to-band tunneling has not been reported so far in such devices. However, we looked at devices not in the 10 to 20 per cubic centimeters, but in 10 to 18 per cubic centimeters with a boron more than phosphorus. Atomistically, the picture is shown on the right, and the device structure is shown on the left, very similar to what I've shown so far. But the depletion layer width is on the order of 100 nanometers. This shouldn't, in principle, allow band-to-band tunneling. However, when we look at the room temperature p-n diode characteristics, IA, VA represents effectively IPVP, we observe that for the black curve, when V sub is 0, the reverse bias current is very low, and the forward bias current is relatively high. This is typical characteristics of a PN diode. But we can change V sub, and we can activate, in fact, the reverse bias current up to very high levels. So we can observe that high reverse bias current can be induced by tuning the V sub to positive values. In forward bias, we can look at IA V sub, and it's not much change. But in the reverse bias, we can notice that V sub drastically changes the current from practically no current on the negative voltage to high current in the positive voltages. So with that said, it is important to understand that band-to-band tunneling can be used to activate can be activated by the substrate voltage as a backgate. So finally, I wanted to just show you how this happens. When we don't apply a V sub, this on the right should be the band diagram that we are dealing with. The Fermi levels are in the band gap. There is no possibility for tunneling from one side to the other. But if we apply a positive V sub, we can actually modulate this potential and lower it so much that the electrons from the valence band on the left could be able to tunnel to the right. This is not the case when we apply negative V sub, specifically because this bottleneck on the right, which is activated at negative V sub, is wider than at positive V sub. That's because the N side is lower doping. So when we have a relatively larger depletion layer width on the right, we cannot activate the band-to-band tunneling current. So this result was published actually this month in Japanese Journal of Applied Physics, together with collaborators from University of Indonesia. So this gives us the possibility to address, even in lower concentration devices, interesting phenomena of band-to-band tunneling. So let me very briefly show you the summary. We report here transport through pairs of donors and acceptors. It can give strong current enhancement, but unfortunately it's difficult to control. Nevertheless, it allows us to think of a basic concept of atomistic tunnel diodes. A second result reported the clusters of donor atoms working as quantum dots. This is statistically more likely, and we can understand it by donor-acceptor compensation concept, and also by considering the disorder in nanoscale. And that gives us the possibility of single charge tunneling effects, another fundamental effect. Finally, moving away from high concentration into low concentration devices, we can use the substrate voltage to activate band-to-band tunneling, and that gives us less design restrictions. I think these topics cover the possibilities of addressing or probing new properties of highly doped and highly co-doped silicon, as well as new functionalities for band-to-band tunneling devices. So I'd like to thank our collaborators who contributed to this work, and thank you for your kind attention.
Thank you very much, Professor Morel. The time is passing to the scheduled time. So just we can have one or two questions, very brief question. If there is a comment or question, please. So from my side, I have a question about the state, P state or boron states. Can you show the slide number, maybe 9 or 10? The first one, first
yes.
Topic. Oh, that is 9, please 9, give the slide of 9. Yes, yeah, it's okay. And in this case, the boron states and the phosphorus states are becoming deeper when the structure is becoming two-dimensional. And then my question is, now the result of a compensation, the P state and boron, phosphorus state and boron states, phosphorus state is filled state, and boron state is empty state. Correct? Right?
Yes. in terms of electron charge occupation, right?
Yes. And so that means the phosphorus state is already filled. So coming the electron from electrode, that is, I think, very difficult. Even so,
Yes.
how do you think about that the energy level is shifting? If something happened, then it may shift a little bit.
I think this is a very reasonable question. When phosphorus level is below the Fermi level, it should be occupied with the electron. But this is a dynamic transport mode. So we have empty states on the left. So electrons from the phosphorus will actually be moved towards the boron. And then from there, they will be collected to the p side. So then the phosphorus is for instantaneously empty again. And it will be populated most likely with electrons from the n-side region.
That is my question is there any shift after moving the electron toward the boron state? Just to keep
So,
the position.
Yes, it's a kind of a charging energy, because when the electron is inside the phosphorus donor, the potential is lifted up and no other electrons can be entering. And when the electron moves away towards the boron side, then the potential is relaxed again, and it can be allowing again the new electron to come in. So this is specifically, we don't understand yet how this really works, because what I just explained is kind of single electron tunneling. But if it is a resonant tunneling or another type of tunneling through the hybrid phosphorus-boron states, we are still trying to understand that from ab initio simulations.
Okay, thank you very much.
Thank you.
Is there any other very short question? Yes, Professor Ikeda, just a short question, comments.
Okay, thank you. Please show me, I think you showed the comparison between the experiment and theoretical Coulomb diamond.
Yes.
Number 16.
16, yes.
When you calculated the Coulomb diamond, you put some capacitor values.
Yeah.
Their values are valid for the expected values from the co-dopant case.
So with Garan-san, yes, we tried to match this kind of picture that we have here, more or less. So the resistance on the right is very low. The resistance on the left is relatively high for single electron tunneling, and capacitance is considered the silicon of a few nanometers only. And so also the dopant cluster size is also taken into account when we define C sub. So it is trying to be matching the experiment, but of course there is some room for optimization.
Okay, thank you very much.
So thank you very much, Professor Morale. So let me move to the second presentation, invited lecture presentation. The second presentation is given by Dr. Yi-Fei Wang, Assistant Professor of Research Center for Organic Electronics, Yamagata University. And he graduated from Department of Electronics and Applied Physics at Tokyo Institute of Technology, Japan in 2017.
入りました？入りない。今どこに入ろうとしてます？
Sorry. His research interests are in electronic materials and printed flexible and stretchable electronics and wearable healthcare and robotic tactile. So, Dr. Yi-Fei Wang, could you start the presentation?
Okay. Thank you very much, Professor Shimomura. And okay. So can you see my slide in full screen?
Okay, now we can see the slides, but it is like the second
Okay.
monitor view. So,
okay, I will change. Okay. How about now?
it is okay. So please.
Okay.
Presentation.
Good afternoon, everyone. And my name is Yifei Wang. I'm an assistant professor in Yamagata University. And currently I work together with Professor Shizuo Tokido. And it's my pleasure to introduce my work in here. And the title of my presentation today is Flexible Printed Sensor, and from fundamental study and to the practical application. And I will give my talk in the following four parts. Firstly, a brief introduction of our research background, and also the introduction of the printed electronic technology, and then it's our recent development of flexible printed sensing system. And finally, is our perspective and the conclusion. As we all know, currently we are almost entering the internet, the society of Internet of Things. And the sensors will play the key role in the IoT society. And the sensor applied in the manufacturing and can monitor in the machine in the factory, and also can monitor in the planet, and also in the intelligent car and robot. And the sensor can also offer them the sense of feeling. And also when the sensor applied to the logistic and transportation, and we can very easily to tracking the delivery information of the goods, and also the safety information of the food. And also another very big application is also the healthcare and the medical. And currently maybe already many commercial wearable devices to give on-body monitoring or wearable healthcare monitoring. And another is another one of big advantage application of the sensor is also the environment monitoring or intelligent agriculture. So there will be a high demand for the sensors, and they have reported mentioned there will be very soon 1 trillion of sensor connected per year, and at the year of 2025. So they have a big requirement for sensors such as biosensor and the force sensor, and all the temperature sensor, humidity sensor, and as well as the chemical sensor. And all these sensors will need to be low cost and small size and high performance, and as well as low power consumption. So how to achieve this type of target? And in here we give our own solution, a printed flexible sensing system. And the concept of this sensing system is a combination of the advantages of organic and inorganic materials, and the advantage of printing process, and also as well as the current the mature technology of silicon-based electronics. And by using the printed sensing materials and technology, and we can develop various of sensing materials. And also these materials can be turning the electricity and also sensing property. And by using the printing process, and we can produce these sensors with a high reproducibility and very high uniformity. And printing also can bridge the gap between the lab-based fabrication, and also between lab-based fabrication and industrial manufacturing. And another part, we also use the advantage of the mature silicon-based electronics, and we use the chips and the amplifier to do the single treatment and the single process. And this can offer us the device very high density and high functionality, and also it's compatible with the standard open network. And also we also try and develop this type of circuit by using the printing process, and it can fabricate on the soft or even stretchable substrate, and also it can fabricate using low temperature process and with low cost. So why the printing technology can offer us such big advantage? And in here I show some information of the current available printing method. And in the left side figure, currently already many different type of print technology developed, like screen printing, dispenser, gravure offset printing, and flexo and inkjet, and even the reverse offset printing. And this different type of printing method can produce the film with the thickness covered from several tens of nanometer to several tens of micrometer. And also the resolution can be as high as to reach the sub-micro scale. And the right side is the materials, required viscosity of materials available for the printing process. We can see it's by use different printing method, we can use materials cover the quite a wide range of viscosity. So that means many of the material, like many different type of viscosity materials, we can develop the ink. And then I'd like to give a simple introduce of some typical printing method. Firstly is a well-known inkjet printing. So this is a kind of we call on-demand additive process. And the functional ink like metal nanoparticle, or like the semiconductor polymer or small molecule semiconductor, and the solution of these materials can filled in the ink cartridge and then printed on the target substrate by using the digital design pattern. And by using inkjet printing, we can very quick to realize the circuit we design. And in here, we also show a figure and the circuit we developed by using inkjet printing on the flexible substrate. And actually, by adjust the printing parameter, we can very easily to fabricate the OTFT array for with the channel length and as short as 10 micrometer. And if we need more high resolution, we also can use another printing technology, the reverse offset printing. And the printing process was shown in here, and we can see firstly the ink was coated on the blanket, and then the ink film was patterned by using the printing plate, and then the remaining pattern on the blanket was transferred on the target substrate. By using this method, we can achieve very high resolution feature of the electrode. And in this page, we can realize the source and drain electrode with a distance as short as 600 nanometer. And also, this method can be very easily to fabricate the highly integrated circuit. And also, another advantage for this method is we can fabricate the electrode film with quite a flat surface and also the shape, very sharp edge. This is the fact. This is the reverse offset printing, and then we also have another printing method is we call screen printing. It's quite most mature and low cost printing method. And in here we show the the illustration of the printing process of a screen printer, and ink was firstly played on the screen mask, and then it was used the sketch and was coated through the open area of the screen mask, and then transported to the substrate. And by using now actually already many screen printing machine, by using this equipment, we can fabricate the sensors with very quite high speed and also even with large scale. And the resolution of the screen printing is not as high as the resource printing, but still can reach the resolution of 50 micrometer. So it already can afford many afford many requirements from the fabrication of sensors. And then I will introduce of our developed printed sensing system. And our system was constructed by the printing sensors and also a silicon-based circuit and to do the single amplification and the noise reduction. And also this data was transmitted to the computer or smartphone by using BLE or NFC. And this system was, as I mentioned before, it's actually the combination of the organic electronics and the silicon-based electronics, and use the organic material, use the printed materials. We can make sensors to sensing optical pressure or even temperature, and some biomolecule or some air, and with very high sensitivity and high selectivity. And also with the silicon-based circuit, we can do very good signal amplification and noise reducing. This is this is the structure of our sensing system. And firstly, I wanted to introduce some of our recent work by developing the new type of sensors. Firstly, the printed temperature sensor, and in here we use a conductive polymer named B.PSS, and this type of polymer have a thermoactive hopping transport. So in this case, its conductivity can be influenced by the temperature change. But one of the challenges of the B.PSS materials is it is a hydrophilic polymer. It's a water-soluble polymer, so it's always very easily to affected by the humidity in the environment. So in our new ink system, and we using the cross-linker named GOPS to enhance its humidity stability. And also we use a surfactant named TX100 and to improve the printing property. And after developing ink, we fabricate a fully printed flexible temperature sensor. And the electrode made by inkjet printing, and the sensing layer was printing by dispenser, and also then a fluorine-based polymer used as a passivation layer, also realized by dispenser printing. And then we can see here I show the performance of our developed flexible sensor. And when the humidity range changed from 30 to 80, and it's almost no change of response of our sensor. So it's show a very very stable temperature sensing performance. So that means we realized a humidity stable temperature sensor. And also this sensor show very good cyclic stability. And when we change the temperature from 30 to 45, it's give very stable output. And also the temperature range of 30 to 45 very perfectly covered the human body temperature range. So it can use for as a kind of healthcare device. And then we also developed a printed stretchable strength sensor, and by using a novel developed brittle stretchable conductive network. And this sensor was constructed by using a silicon-based substrate and also a stretchable conductor and also a brittle conductor. And the sensing mechanism is can be very easy to understand. And the brittle conductor layer is very easy to generate some crackle when we stretch the film. So in that case, it will give a very big resistance change. So it can offer us a very high sensitivity. And then the bottom layer, we use a stretchable conductor. This layer, the conductivity was lower than the brittle layer, but still can keep a very good conductive at the high, even at the high stretch condition. So in that case, the device can keep working until even at a very big strain. So this sensor can stretch to 100%, and also this sensor was realized by Foley screen printing process. And design in here, we show the performance of our developed sensor in the figure A, and we can see if we only use the operator layer like a metal film, and the device will fail to conduct it at a very low strain of about 5%. And if we use only stretchable conductor, and we can, of course, we can go to very high stretchability, but the sensitivity is quite low. When we're using our new developed Pareto stretchable conductive network, and we can see our sensor achieved both high sensitivity and a wide sensing range. And also this sensor show very good linearity and quite low hysteresis as shown in figure B. We also make a compare of our device and with the recent reported stretchable strength sensors based on different material system. And we can see our sensor have the advantage in both have a high sensitivity and a wide working range. And this is a development of the stretchable strength sensor. And here is a demonstration of our sensor application on the robot. You can see the sensor was attached on a soft robot gripper. And when the robot finger bending, we can see a very obvious and very stable output signal. So this can be applied in the future for the robot. And another is we also trying to develop a new conductive composite. And the conventional conductive composite usually by just using the conductive filler and with some soft polymer and with a random dispersed system. But this type of composite usually have limited conductive pathway and always need a very high filler loading, and also the fabricated sensor always show big hysteresis and also low sensitivity. So in our work, we successfully developed a porous conductive composite with a segregated conductive pathway, as shown in the right side figure. And this type of new composite can realize high conductivity at a very low loading of conductive filler, and also the sensor fabricated by this device, by this composite, and with have very low hysteresis and also show very high sensitivity. And this work is still under review, still in summation. So in here, I not put so many details, but we also can see some devices fabricated based on this composite. And the first show very good anisotropic bending sensing performance. And when the sensor outer bending, so they have a tensile strain applied on the sensor, and we can see they have an increase of the resistance. And when the sensor was inner bending, so it's a compressive strain applied to the sensor, and we can see a decrease in the resistance. And also it shows very high sensitivity and also very good linearity. And for application of this type of sensors, one of the simple demonstration is we can use this to monitoring the movement of the finger. If the sensor, because it's flexible, so it can attach very easily attach on our hand and to monitoring the bending. And another is we also can monitoring the bending state of a soft gripper. And then this type of composite also can be applied as a pressure sensor. And we can see that we already fabricated the pressure sensor, single sensor, even also the single array. And this sensor, when we attach a finger, give a gentle press or the hard press, it can give a very stable output. And another application also very interesting is for the robot. And when attached on the robot, and when the robot grabber and handling the object, it can give a very clear monitoring. And here is a simple demonstration. And when the egg was grasping by a robot hand, and we can see very clearly signal. So this sensor can be used to develop a feedback system for the robot. And this is the development of the sensor. And as we mentioned, sensor not only the sensing system, not only include sensor, but also include the signal process unit and also single transmission part. And so in our laboratory, we also develop a printed flexible hybrid electronics. And this circuit was developed by printing, and also we use the silicon chips and by using the surface mounting technology. And here is a cross-section of the circuit we developed. And we can see the sensor was directly fabricated on the substrate, and also we also developed a two-layer conductive, a two-layer flexible conductor by using one layer stretchable conductor and another layer high conductive conductor. In that case, we can realize a highly flexible and high conductive circuit. And also, they also have very good bonding stability with the silicon chips. And we successfully developed already the NFC type and the BLE type. And also in the future, we also trying to more complex circuit with more function. And here is we already successed one of the sensor patch with our developed printing sensor and our printed hybrid circuit. And then it can use to directly attach on the skin to detecting the body temperature. You can see a sensor was attached on the arm, and then when we start, and we can see the signal the temperature signal was directly displayed on the mobile phone. So this sensor have potential to directly applied as wearable healthcare devices. And another is we also can use this type of sensor to monitoring the temperature change of the object. And here, when we add hot water in the cup, and then when the temperature slightly increase, and this sensor also can give a very clear monitoring. So this is one of the potential application in the IoTs. And so for the future perspective, after we develop this type of sensor, and of course, one of the very big application is for healthcare. And we can develop the flexible sensor system. We can put this sensor on the bed or wearable or attach on our body, and to give to give a continual monitoring of our health condition. Actually, one of the product named White2Bits actually already commercially available in last year. This device was realized or developed by our laboratory. And we hope this type of, with the development of printed sensing system, and we can realize more safety and more efficient and more convenient healthcare. And another big advantage, and we are big advantage of our developed sensor is to apply it to the to smart logistic and transportation. And we actually currently we already developed the temperature sensor and the humidity sensor, and even the accelerator sensor, and the true detection temperature, humidity, and the impact of the object of the product during the transport and the delivery process. And in this case, we can how to say more, we can keep a very detailed information of the product, like a temperature, storage temperature, or the humidity, to make sure the safety, and also it can always trace the position of the trace the position of the product, and also available for the delivery process. So at last, and I'd like to give a short conclusion. Is by utilizing the advantage of our functional materials and also the printing technology, and we can develop the sensor with the features of thin and lightweight, and also flexible and even stretchable. And also we can manufacture this type of the sensor with a very low cost. And also, they have many different type of sensor we can fabricate by using our printing technology. And in the future, we expected our sensor can be used in medical healthcare and even the robots, and as well as the everywhere, and to contribute the society 5.0. And at last, I'd like to give a brief introduce of our group. And our group is actually the member of our group include the staff and students, as well as the researcher from company. And the population of our group is almost over 100. And we are very expected to the researchers from all over the world to visit us after the corona. And so this is my presentation of this time. And thanks for your kind attention. And if you have some question or comment, you're welcome. Thank you.
Thank you very much, Dr. Wang. So now the session is open to discussion. So first, Dr. Abhay Sagade, please give the question. Comment.
Yes, okay. Thank you, sir. Thank you. This is a very nice talk. My question, I have one or two questions. The first thing is that what is the typical cost of this reverse offset printing tool?
You mean the cost?
Yes, cost.
Yes, actually, the reverse offset printing is depends on the pattern, and the most cost part is the printing plate. And now we ask some company to make this type of printing plate. So if very high resolution, so that have a relative high cost. So that means, so in that case, we how to say, we only in some expensive device or some important device we use this type of printing method. So it's a relative high cost. Yeah.
Yeah. So if we, let's say, if we want to obtain like 1 micrometer feature size.
Yes.
So then what will be the cost at approximately?
Actually, we're using this. How to say, we fabricate, when we fabricate the TFT, we use this type of printing method. And currently, sometimes depends on the company situation. We like one printing plate, yearly maybe $3,000. Yeah, it's quite.
Okay.
Yeah.
Yeah. Right. So can you go to slide number 16?
16. Okay. Oh, okay. This one.
Yes. So I believe that the gauge factor is actually a change in resistance divided by applied strain.
Yes, applied. Yes.
Yeah. So I can see actually that value of 870 is actually only delta R by R0 and not divided by strain. Am I correct?
Yeah.
The value of,
sorry, I not. Can you repeat the question?
So value of 870
Mm-hmm.
is the value of
Mm-hmm.
a gauge factor or only delta R by R0?
Yeah, I think
Because it is supposed to be a slope of graph A, isn't it?
I see. Actually, in this figure, I showed the gauge factor is the relative resistance change. Yeah, the 800. Actually, the sensing range of our device is about 100%. So after divided by the strain range of 100%, so it keep a gauge factor of about 870. That is we calculate by using this method. And actually, because our sensor have very good linearity, so we think the gauge factor should be 870.
Okay, so there is small non-linearity in this red curve, so that can be called as a negligible variation.
I see. Yeah, thank you for your comments. Yeah.
Okay. So the last question. So
sorry, time is very
okay.
late. So
Yes. Okay. Thank you. No problem.
James, sorry.
Nice.
So,
thank you.
Thank you very much, Dr. Wan, for the very nice presentation. So we would like to move to the contributed lectures. Thank you.
Thank you. Thank you very much.
So the next presentation is Dr. Madhupriya Samantha. The presentation title is Enhanced Electric Field Assisted Electron Emission from MOS to Decorated Amorphous Carbon Nanotube. So could you start the presentation?
Yes, sir. So is it visible?
Yes, you can see.
Am I audible, sir?
Yeah, we can hear you.
Okay, sir. Myself, Madhupriya Shamanto from Jadavpur University. Good afternoon, all everybody. I am going to present my one of the research topic, that is enhanced electric field assisted electron emission from MOSE2 decorated amorphous carbon nanotubes. I have carried out this research work in the thin film and nanoscience laboratory under the supervision of Dr. K.K. Chattopadhyay. Now, these are my plan of talk. First, introduction, then synthesis, characterization, and finally, the results and discussion and the application of the synthesized material. Now, first, what is field emission? Electrons can be emitted from a material into vacuum by three kinds of process. One is thermionic emission, another is photo emission, and the other is field electron emission. Now, here we are focusing on the field assisted electron emission, which is the electron is emitted from the material surface into the vacuum by the application of electric field. It is also known as cold emission, as there is no thermal energy is required to emit the electron. One-dimensional nanostructures are also the efficient field emitter. Now, here we are focusing on the field emission properties of some kind of core shell type of heterostructure, that is two-dimensional MOSE2 decorated over the surface of amorphous carbon nanotube. Now, first, I have synthesized the we have synthesized the core shell type, the MOSE2 decorated amorphous carbon nanotubes. First, amorphous carbon nanotube is synthesized via standard procedure followed by our earlier works. using ferrocene and ammonium chloride. Now, after that, we have used the 30 mg of prepared amorphous CNT for the formation of MOSE2 nanoflakes over the surface of amorphous CNT under low temperature hydrothermal process. Now, after the collection of powder from the hydrothermal process, it is again annealed at nitrogen atmosphere 450 degrees centigrade. And also the pure MOSE2 powder is also synthesized for comparison using the same procedure. Now, here we have shown the XRD pattern of both the synthesized materials, and for the hump between 10 to 30 degree, 2 theta 10 to 30 degree corresponds to the amorphous nature of the amorphous carbon nanotube, and other indexed peaks corresponds to the proper formation of the MOAC2 nanoflakes, which are exactly matches with the JCPDS card number 290914, and it is the hexagonal phase of the MOAC2. Now, corresponding Raman spectra shows that the standard D and G band proclaims the formation of CNT carbon nanotube, and for heterostructure A1G peak at 242 centimeter inverse corresponds to the formation of MOSE2. Now, these are some morphological FECM images. First, figure A corresponds to the bare carbon nanotubes of inner diameter around 70 to 90 nanometer, and figure B represents the decoration of MOSE2 nanoflakes over the tube, over the carbon nanotubes. Now, these are some TEM images, and from these TEM images, we have found the thickness of the nanoflakes is in the order of 4 to 5 nanometer. Sorry. Back button. Oh. Sorry, sir. Microsoft PowerPoint is not responding.
Okay, completely, it is freezed.
Yes. Actually, Zoom is not responding.
Can you explain the results by words?
Yes, sir. So finally, we have. Okay, sir. Let me try once again.
Do you have any PDF results? PDF file of your results?
Mm,
You can share that also.
okay, sir. Actually, yes, sir.
Yeah, you can start.
So after that, yes, after that, we have measured the electric field assisted electron emission of these three materials, and it is measured at 180 nanometer inter-electrode separation. Now, the current voltage, current electric field current density versus electric field density is plotted in the graph, and it has been found that our ACNT MOSC2 composite heterostructure shows better result than the other two counterparts, and turn-on field at the which is measured at current density 10 microampere per centimeter square. It is downshifted to 5 volt per micrometer for ACNT MOSC2 compared to ACNT, which is around 8.9 volt per micrometer. Now we have plotted the Fowler-Nordheim equation and ln j by e square versus 1 by e, and from the slope of the graph we can calculate the enhancement factor, which can be calculated by the following formula. And after the from the slope of the graph we have found the enhancement factor for CNT MOSC2, and the heterostructure is found as 4353, 4666 and almost 7200 respectively. So our heterostructure outperforms than the other two bare counterparts. Now, we have also simulated these nanostructures with ANSYS Maxwell simulation package. It is evident from the two images that electric field distribution around the around the structures, one is for bare ACNT, another is for MOSC2 decorated ACNT. Now, dense electric field distribution is observed for in case of MOSC2 decorated system, and we have applied this almost same parameters which we have applied in the experimental measurement. Now, finally, we come to the conclusion that our heterostructure is synthesized via low temperature hydrothermal process. Then, different characterization techniques confirms the successful attachment or formation of the hybrid system. Then we have measured the electron emission phenomena for the three samples, and it is confirmed that our heterostructure performs best in case of both turn-on field and enhancement factor. And also finally, the ANSYS simulation suggested that the electric field distribution is much better with respect to in the composite heterostructure with respect to amorphous carbon nanotube. These are some references we have used. Now, finally, DST Inspire, CSIR, and UGC are thankfully acknowledged for financial support and fellowship, and also thankful to the Thin Film and Nanoscience Lab, Jadavpur University. Thank you.
Thank you very much, Dr. Madhuriya. And I think I have a very brief comment. The result is very interesting, and the effect of nanocomposite is very clear. So if you can clarify the interface structure between the carbon nanotube and the
MRC2.
OS2, then it will be more interesting because we are thinking about the strength of the attachment for the electron emitter. Then the strength is also very important because it is has a very high current, I guess.
Yes.
So that if that is becoming clear, then I think it will be a very nice work, I think.
Okay, sir.
Okay, thank you.
Okay.
So the time is limited, so
Okay, sir.
we have to close.
Yes, sir.
Okay, thank you very much.
Okay, sir.
So let me move on to the next one. Next presentation is given by Dr. Pradeep Gupta. The title is Cyclic Loading Response of Nickel Nanowire, a Large-Scale Molecular Dynamics Simulation Study. So please start the presentation.
Is my PPT is visible, sir?
We can see the PPT, but it is not the full screen mode.
Yes, sir.
Oh, okay. Yes.
No.
Okay. Yeah. Yes, please.
Yeah. Thank you very much. My name is Pradeep Gupta. My topic is cyclic loading response of nickel nanowire in large-scale molecular dynamics simulation. In this one, I'm the presenting author, and my co-authors are Dr. Karthik and Dr. Nataraj Jedler. The content will follow as the introduction, the simulation procedure, the boundary condition, the result and discussion, and references. Before actually proceeding here, I like to say that my simulation is still going on, and this is a very small portion of my results I am going to show you right now in a brief manner, because still the simulation is going on. So let me start. The introduction. The nanowires are widely used in the fields of biomedicals and other places, sensors, nano-optical electronics, and a lot of investigation going on regarding the mechanical properties, so that they can be used, whether the tear and wear conditions of these things will go on, and the sensor will be a little long lasting. So until now, there is a lot of mechanical properties of nanowire are still a challenge, because the experimental method to do those things are a little bit difficult, and so many challenges come in that very part, because we have to go for a perfect dimension for those things to get a perfect mechanical properties and other stuff. And so many authors have already done these things. Recently, a molecular dynamics comes, that is not a recently thing, that is in late 80s and late 90s. Molecular dynamics comes in the picture, and they have employed molecular dynamics in various fields. So however, these things now still a very limited work is done in the case of nanowire and its mechanical properties. And we are going to choose here a nano bending test to get the mechanical properties. That's a cyclic bending we are going to do. So yes, before going any further, my simulations are based on molecular dynamic simulation. And before going any further, I like to just give you a brief introduction regarding what is molecular dynamic simulations are here, so that rest of the participants can understand what is the molecular dynamics is going on. That is, we are here creating atoms, and atoms are interacting with other atoms in a form of, we are in this very fashion. We can see that that's the first atom, so atom 1, atom 2, and atom 3, and how they are interacting, how their different uh, location is changing with the use of velocities and other stuffs. So in this very fashion, we are seeing how the atoms are moving forward by using the Newton integration equation method motion here. So we can, flow chart is already given how we are assigning, where initially we are assigning, we set the particle position, then assign the particle velocity, and each forces of each particles are calculated, and updating the particle position. We are recording those things and and updating the particle position and velocity to the next time, next step, and after that we save that particular positions also there. And if our simulation is done, then we are going to save the final and go for the analysis. If our simulation is still going on, then we will go further and calculate the forces, and that cycle will continue again and again here. So here is the simulation procedure we are going to use here. There is a nanowire in a representative form here. We are representing here, and there is a spherical indenter we are using, and we are forcing that spherical indenter on the nanowire in such a manner that that nanowire will go a little down. We are applying certain distance with a certain force. Loading rate is already given, that is the ranges from uh, 0.8 to 1.5 angstrom per picoseconds, and that is in cyclic nature. We will go for around 10 angstrom, then again we will increase the indentation depth again. So first we are going to load the nanowire, and after that we will go for the unloading condition, and this will continue till around, we are actually going for around 5 cycles, so that we can see how the nanowire is going to respond in this one. So this is the boundary condition we are using here is SSS, and the sample is this one, and assembles is this. The number of atoms we are using here is 925000. The loading rate 0.8 to 1.5, and simulation temperature we are using here is 300K. My results are very actually that's in a very initial position. Still the simulation is going on under for simulation is going on. So whatever the results we have, we are putting all those things in this area. In the present study, we reported the molecular dynamics MD simulations studies carry out on the nickel nanowires subjected to the nickel loading, cyclic loading. The nano indentation technique is used to carry out the cyclic loading here. The nickel model comprise of around 92 920,000 atoms, and interactions are models using the embedded atom method potentials. The simulations are performed at a constant temperature of 300 Kelvin, and loading rate is ranges from 0.8 angstrom per picosecond to 1.5 angstrom per picoseconds, and up to the 5 cycles here. A virtual spherical diamond intender of a sphere of around a sphere of 100 angstrom is used to apply the load on the nickel nanowire from the MD results, and we observe that the nano wire of the existing what initial results we got here the exhibits the strain hardening from 300 nanonewton to 600 nanonewton behavior, which increases the number of cycle. This is attributed to an increase in the dislocation density, and moreover, as the loading rate increases the initial load and increases the after every cycles of deformation. Here is a few results I have included here. That is the load displacement response of the cyclic loading of the nickel nanowire at a different cycles here. The cycles here C1, C2, C3, C4, and C5, it is represented as a cycle. And this is the different multiple colors I have used. The initial color, for C1, the black color is for the loading and red color is for the unloading, and vice versa we have used here. We can see there is a load is increases continuously from C1 to C5, we can see, and we are expecting a similar kind of result we are going to get in our results there. So these are the references we are going to use, we are using here. Thank you.
Okay, thank you very much. Now the session is open for discussion. Is there any question, comments? Is there any question or comments? Okay, from my side, I would like to know the relationship between your result and the experimental result.
Yes, sir. Actually, yes, sir. Actually, till now, nickel nanowire experimental work is not done. So that is the reason we are not able to compare, but other similar results are available there with the composite and alloys are there. So we can compare in that very nature. Yes, sir. So initially, actually, simulations are still going on, because from last 1 month the simulations are going on still. So whatever that is a small scale reason we have used, and whatever the results we got, based on that we have plotted this result. So that is the thing, sir. We are expecting that the results we are going to get, there will be a trend follow, and that can be comparable with the experimental results, sir.
Okay. Thank you very much.
Thank you, sir.
Thank you very much, Dr. Pradeep. So, let us move on to the final presentation in this session. So next presentation is given by Dr. Sornai Watanaga. The title is the dual phase xenon time projection chamber simulated in Grant 4 to detect neutrino-less double beta decays and WIMPs, weakly interacting massive particles. So please start the presentation.
You'll have to, yeah, fine. Good afternoon. Hello.
Hello, yeah, we can hear you. So
yeah, fine. Thank you so much for the conference organizers for giving me this opportunity. The content of my talk is going to be an introduction, which is based on the motivation and the objectives, and the methodology is about the xenon time projection chamber and the results. We are actually a lab in the Dalberg Educational Institute where we do GAN4 simulations, and we do this so that the students get a feel of what is going on in high energy physics. And there is a lab here by the name of DISA, which is Dalberg Educational Air Shower Array. So we are basically into array physics, and this is like learning GAN4. So one of the students has done this work, but because of this pandemic, we do not have the students now coming for the classes regularly. So I had to give the presentation. But it's a very interesting work that the student did. This was on dark matter studies, where we have a lot many efforts going on to understand what is dark matter, and so there was a call for new and improved methods to spot this mysterious substance. And generally, the dark matter searches use detectors based on liquefied noble gases such as xenon and argon, having a lot of potential. And we tried to do this simulation in GIN4. So the literature in this survey that we did was that we had this experiment going on, Global Argon Dark Matter Collaboration, which was formed in September 17 and comprises of many scientists. And they were working with this ARDM labs in Spain, then Dark Side 50 experiment in IFN Italy, and then Mini Clean at Snowball in Canada. And this was an article by this group where they were working towards immediate deployment of dark matter detector. So one well-considered form of dark matter was that matches astronomical measurements is weakly interacting massive particles, which would exist in our galaxy with defined numbers and velocities. This is one of the experimental work which is going on. In dark matter experiments, they were employing liquid argon detectors. Such particles, which are the WIMPs, would collide with argon nuclei. These are the rare gas, causing them to recoil. And these nuclear recoils produce ionized and excited argon atoms, which after a series of reactions form short-lived argon dimers, which decay and emit scintillation light. So the emission and the decay and the emission of the scintillation light is the signal that this may be the nuclear recoil due to a WIMP. So the time profile of the scintillation light is significantly different from what is created by argon ionizing events associated with radioactivity in the detector material, and hence this has been shown to be have a very strong rejection of the background sources, this method. And so this is done on the basis of pulse discrimination technique. So the dark matter candidates for an introduction are many. We have dark stars, massive quark stars, nachos. Then we have new techniques to detect density of dark matter. Neutrinos also a candidate, WIMP, and then axions. Vacuum energy density is also related to existence of dark matter and galaxy formation. So these are the many possible candidates for dark matter. So in this study, the objectives were to study the xenon time projection chamber, simulate the xenon time projection chamber using Monte Carlo based GAN4, and validate the simulation. Now, why is validation important? Because in this paper, most important is validation, which is like I have results from some experiment conducted somewhere, and then I validate it in my simulation. Then I know I am on the right track. So the methodology, GAN4, I hope somebody must have heard of this at least. It is an open software provided by CERN, and it is downloadable, installable, but a huge amount of work goes into it. And it is a toolkit for simulating the passage of particles through matter. And these are the processes which we take place, and it involves a lot of coding in C++. So GAN4 is, now what did we go and do is we first design the detector, then the material we have to define what you want in the detector, then the physics is defined based on the processes defined in the toolkit, but we have to define them in the physics. And the simulation is finally what do you want, which is what do you want out of the simulation. So these are this is how we define the detector, and then we are looking for the material, and then this is the physics involved and the simulation. So here the detector construction that we did in GAN4 was define the geometry. So this is how we do it. The dimensions have to be defined, the elements have to be defined, and the material finally has to be constructed. But our material was different. So we had these xenons to define, and then you have physical and logical volumes which you have to define. This is a small picture of that. So finally we had to, this is the time projection chamber which we have first. Initially we came out with the time projection chamber, then a modified version was the liquid xenon time projection chamber, and finally we have the dual phase xenon time projection chamber, where the detector contains, this is the gaseous xenon and the liquid xenon. At the top, the gas is in the top and the liquid in the bottom, and they're separated by a mirror. The incoming particle induces electron or nuclear recoils in the xenon and produces scintillation and ionization signals, as explained, but I'll come to the details here. Now, this is important because why do we use xenon, liquid xenon? So because the high atomic number and high density of xenon makes it very efficient to stop penetrating radiation, and this gives rise to a self-shielding, so property of liquid xenon, and absorbs gamma radiations effectively. So most important is how do we hide or overcome the background? How do we have a signal to background ratio, a good one? So background from the experiment surroundings, the detector construction materials will interact freely in the outer parts of the detector, leaving the inner region nearly background free. So the inner region of the target with low background is used for the rare decays. Obviously, I do not know where the decay is going to take place, but then we are looking for signals which are coming from the almost from the central region of the detector. So due to the high density, and then what are we looking at? We're looking at the energy loss dE by dx in the liquid xenon, and it is different for electron recoils and for nuclear recoils. So electron recoils is from any background radiation, whereas nuclear is from the event or the rare event that we are looking for. And the scintillation light is S1 and S2. So S1 is the scintillation and the electroluminescence light is S2, which is separated by a PMT, photomultiplier tube, and the ratio of S1 to S2 is then taken for the two different events, and these are the parameters that we record and then we assess. So these are the processes happening, ionization and scintillation process in the liquid xenon. And we are trying to look for neutrino-less double beta decay, where you have two neutrons decaying into two protons, and simultaneously emitting two electrons from the W minus boson. And this decay has a half-life of approximately 10 to the power 25 years. Experimentally, it hasn't been observed till yet, but this is a rare decay, and we're still looking for it and trying to design detectors which are sensitive to this decay. So this is the visualization of the detector that we had designed. This is the PMT, this is the gas. So this part is enlarged here and this part is enlarged here. This is the gaseous xenon, the green one, and this is the liquid xenon. The liquid xenon is this, and we have the electric field rings also. This is the source holder inside this area, inside the liquid gas detector, where we have the source kept here also. So we had a source kept there so we could take background signals and then identify them, and we had without the source also. So the data that we generated was for the gamma hits, which were from 70 kilo electron volts, very small energy, to 100 kilo electron volts, alpha particle hits, and neutron hits. We did it, the simulations were performed for three different energy particles. So the exercises that we did in this work was the primary particle, which was these three, energy versus the scintillation yield. So we plotted this, and then we saw whether the energy was conserved, what are we hitting at, what is the emission signal, and how much energy is absorbed by the medium. And then there was another independent study performed, which was position dependent study of the scintillation yield. But this we were able to do only with gamma particles. One of the tables that I'm showing here is for the use of the gamma particle, where this is the gamma, this is the source energy, this is the electron in recoil energy, and these are the photons produced in the simulation. Correspondingly, this is in kilo electron volts, and this is the theoretical value from the reference paper that we have compared. So we have some large variation in these three here, but then we have a comparative good comparable value in the lower energy sources. And then this work was done to study this kind of a detector and what is rare physics processes, how can we detect them. And we have seen that detector is sensitive for the massless particle, charged particle, as well as for neutron. Because see, gamma, we had three particles for the same reason. And then gamma shows the inelastic scattering only. For alpha and neutrons, both elastic and inelastic scattering was also there present. And the beta decay and double beta can be studied with the help of this detector. And this detector, it detects the electrons generated in different processes and weakly interacting particles, which we assume it's going to do. So this was just a simulation study. These are the references that we had. Thank you. And I'm open for the questions.
Thank you for the presentation. So now we are moving to the question and comments part. Is there any question, comments?
Yeah, so can I ask one question?
Yes, please.
Yes.
Yeah. So what are the difficulties with the neutrino-less beta decay when you're coming to the experiment?
That's because it's a rare decay. And again, it's the same difficulty that we had in Kamiokande when you had to observe neutrinos. It was the same level. You had to have a huge signal as compared to the background. And the background is so large, so they had to go underground and do it. Here, the decay is rare in itself. This is a very rare decay. And so the probability of this happening is, like you've seen, the half-life is 10 to the power 25 years. So this is going to have, need to have a huge amount of volume, liquid xenon assembly, where you can think that you may see it. See, when you have a rare decay, then either you have a huge primary gas structure where you can see it. It was same as neutrino problem. Neutrino detection was so difficult. Why? Because neutrinos do not interact. Similarly, even neutrinoless beta decay, this is a rare thing. So there are no neutrinos coming out, and there is only this the proton and the electron, and you have two neutrinos decaying simultaneously. So that's also a very rare thing. So this you can appreciate if we understand what was the background behind these neutrino experiments. So it's the same thing here. It's a very difficult observation, and we've not been able to see it till yet.
So how about that overall cross section that you are observing from xenon? So let us say you have any substitute for that if you say that you want to see that such decays in that sense.
The cross section is very small, and we don't have a substitute. We are trying to now simulate and make experiments, because this collaboration in 2017 is actually trying to set up. Dharma is being set up. There are many experiments all over the world which are being set up just to understand these rare decays and observe neutrino interactions and neutrino oscillations. So this is like a very low cross section interactions that we are now going towards them. Experimentally, we are moving towards them.
Okay, thank you.
Is there any other comments, questions?
I have a query. Masaru Shimomura, you are from this. I mean, you be part of the host institute.
I'm belonging to the Shizuoka University Research Institute of Electronics. Maybe the different person, I guess.
Why? Because in case you are not from the country, then you must be having ideas about these experiments going on. I do not know. Are you from our country, or are you from your host institute in Japan, wherever? What is it?
I'm sorry.
He's from Japan.
I'm not a specialist of the.
Yeah, fine. So you are from Japan. So even in Japan, you have experiments going on in this in neutrino oscillations. I mean, people coming
I think you need to look
parts of
into
the
that.
world will know about these
They
experiments.
are using gadolinium also. So
Yeah, they're
they have
using gadolinium. Absolutely right.
using gadolinium. So
Absolutely.
they have actually within the old super like Kamekande. So they have prepared a balloon. Actually, they are doing an experiment there.
Yeah.
So I
No,
think
I just wanted
not
to
all the
understand
people
that
are
my
aware
host
of that.
understands what am I talking of. That's it. Nothing else.
Yeah.
Fine. Thank you.
Okay, thank you very much. So now I'd like to close the session. Thank you very much for attending the session. Thank you. Thank you, Dr. Rohit. Dr. Rohit, unmute, please.
So on behalf of organizing committee, I would like to thank Professor Masaru Shimomura. Okay, so I hope that this interaction had been quite useful to all of you, so those who have attended. So thank you very much, sir. So thank you all the attendees. Thank you very much.
Thank you
We
very
are
much.
closing the session now. Thank you.